how the arrangement, series or parallel affects the current, the amount of current that is passing through them. Now let's talk about voltage, specifically voltage drops. Here we have two situations. On the first one, we have a pipe that is uniform in diameter all throughout. You have the pressure gauge here to tell us how much pressure is being used to make the water flow from this side to the other side. On the second pipe, we have a situation where it got narrower. There's a section where it is narrower around towards the end. And we also have your pressure bulb. So if you have the same amount of water, which one would be easier to push? Is it on the pipe A or along pipe B? Where do you think would be pressure lesser? Where would you need a lesser pressure requirement? So obviously it would be harder to push your water on the second pipe because there's a narrow section, right? You have to squeeze your water through the narrow section. So you would spend, there's a greater pressure requirement for you to push the same amount of water through pipe B. In circuit terms, that is called voltage drop. More energy is spent pushing the same amount of water through a narrower pipe. Okay, so if you have more resistance, that is more voltage drop. When I say voltage drop, there would be a decrease in voltage. Some energy would be spent. More energy would be spent if the current is passing through your resistor, especially if it has high resistances. Okay, we can understand this even better if we look at this slide analogy. Okay, so here my charges have, we can say that it is high energy at the top and low energy at the bottom, or 0 volts. If we have 60 volts here at the top, when it reached the bottom, it would have spent all of the voltages. The voltage here would be 0 volts. Okay, and the slides would represent my resistances or my resistors. Here, that means that as I am going down, as the balls here are going down, it is losing voltages or energy. Okay, from let's say 60 volts to 0 volts. Let's say, for example, that I have a slide that looks like this. So you have the first slide here and the second slide here. Before you can reach the bottom. This represents my resistors. So I have two resistors in series, right? The first one here and the second one here. The charges or the balls have to pass through all of them for them to reach the top, from the top to the bottom. Okay, so some of the energy would be spent, right, when it passed through the first slide, and then the rest of the energy would be spent for it to be able to reach the bottom through the second slide. Okay, so half of the energy would be spent here and the other half would be spent here. So let's say if you have 60 volts here, the charges would spend 30 volts. There would be a decrease by 30 volts as it passes through the first resistor, and then how much is remaining? 30 volts, right? So if it after it passed through the second resistor on its way back to the negative terminal, the remaining 30 volts would be spent as well. So when it reached the negative terminal, that's 0 volts. Okay, so this is the voltage drop that happens when my resistors are connected in series. Well, what if they are connected in parallel like this? So still the same scenario. At the top of the slide, I have 60 volts, just an example, and at the bottom, my energy would have been all spent from the sliding, and I have 0 volts at the bottom. The main difference here is I have two slides now, right? Because it, let's say in this circuit, in this parallel circuit, I have two branches. So my charges can slide through the first one or the second one. So what I want to highlight here, what's important here is whichever slide the charges chose to pass. This has a resistor in its own. This also have a resistor. They would have spent all of the voltages coming from the top to the bottom, right? So if the charges chose to slide here on the blue one, they have 60 volts here, and they would spend all of the voltages. And when they reach the bottom, that's going to be they are going to have 0 volts left. Okay, energy was consumed all the way down through the slide. But if some of the charges would use the yellow slide, the same thing would happen, right? Their 60 volts here would become 0 volts after they pass through the slide. The voltage drop across resistors in series adds up to the total voltage. So what we mean here is if I have a voltage gain of 60 volts from my battery, that the current or the charges will carry that energy, but when it passed through the first resistor in series, some of the voltages would be spent. There would be a decrease in voltage, let's say 30 volts, and then it still have to pass through the second resistor, right? So here, the remaining 30 volts would be spent. There's another voltage drop here, and so after passing through the second resistor, they have a total voltage of 0. And again, it passed through the battery, so it 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 gains again 60 volts, and the cycle continues like that. So when you are computing for the voltage drops or the energy spent or the decrease in voltage when passing through resistors in series, the formula would be, this is coming from the Ohm's law again, remember? V is equal to I times R. So you would compute for voltage drop across each resistors, right? So V1 is equal to I times R1, V2 is equal to I times R2. When you add all of the voltage drops, you should get 60 in this scenario. It should be equal to the total voltage. Okay? How about in parallel? The voltage drop across any resistor in a parallel connection is equal to the voltage, the total voltage. Okay? So what we mean here is, let's say for example, we still have 60 volts. We have a voltage gain of 60 volts. Some of the charges will pass through R1 and the other through R2. If it chose to pass through R1 or this branch, it should lose all of the voltage gain, right? So that afterwards it has a voltage drop of a total of 60 volts. And then 0 here, and then 60 again when it passed through the battery. But then again, if it chose to pass through the second branch, it should have the same reaction, right? The voltage drop will still also be equal to 60 volts. So it's also 0 after it passes through R2. And then again, voltage gain here. So you actually don't need to compute anything in parallel. What I mean is you don't have to compute for the voltage drop because you just have to look at the given. The voltage drop through R1 is 60 volts. The voltage drop through R2 is also 60 volts. Vn is equal to the total voltage. Okay, let's solve some sample problems. Here, you are asked to get the total current. Your circuit is in series configuration. Your power source is 12 volts of battery, and you have three resistors, R1, R2, and R3, connected in series. Okay, so how much is the total current present in that circuit? Your formula for current is V over R from the Ohm's law. We just put total here. So I guess you still need to figure out your total resistance, right? From the three resistors. So you can compute that. You just have to add them because this is in series. Your total resistance is 30 ohms. Substitute the values. Total voltage is always the rating of your battery. 12 volts over 30 from your computation. Your total current is zero point 0.4 amperes. Okay, let's go to the next one. Again, you have a series circuit. Your total voltage now is 9 volts. And now you have two resistors, 2 and 3 ohms. Instead of asking for the current, you are asked to get the voltage drops across each resistor. How much voltage or energy is spent because it has to pass through the resistor. How much electrical energy is converted to heat because it has to pass through a resistor. Okay, so our formula for voltage drop is V is equal to IR. So you have two equations because you have two resistors. Your currents have to pass through the first one and the second one since they are connected in series. Okay, I guess you don't know your total current first. You need to find out how much current is passing through your circuit. So you need to compute that first. Voltage over resistance. 9 volts over what's my total resistance? I only have to add them because they are in series. Again, if this is in parallel, it's a different story. 9 over 5 is 1.8 amperes. I need this 1.8 to put here in my V1 and V2. Okay, 1.8 times 2, 2 coming from R1. That's my rating for resistor number 1. So how much voltage is spent? 3.6. How much is remaining for 9 volts? V2, 1.8 times 3, that is my second resistor. 5.4. If I add this, I should get 9 volts. The sum of the voltage drops is equal to the voltage gain from the battery. Okay? Does it make sense that I have a larger voltage drop here? Yes, because my resistance is also larger in resistor number 2. Okay? Okay, in sample number 3, we have parallel circuits. My total voltage is 12 volts. I have 3 resistors. R1 is 2, R2 is 4, R3 is 8 ohms. And I need to know how much current is passing through each of the resistors, right? Because the current will get divided on the 3 branches. And how much is the total current? I just have to add them. I will still use I is equal to V over R. I is equal to V over R, V over R. What's different in these calculations would be the resistances, right? Each resistor would have different resistances. So for I1, the current passing through resistor 1 is 6 ohms, 6 amperes. For resistor number 2, the current passing through is 3 amperes. And for resistor number 3, it's 1.5 amperes. Does it make sense that there are more current passing through I1? Yes, because it has the least resistance among the three. And since I3 has the greatest resistance, it has the least current flowing through. To get the total current, I just have to add 6 and 3 and 1.5, and I get 10.5 amperes as my total current. Okay, that was a bit late. Okay, now I also have a parallel circuit. My total voltage is 24 volts, and I have two resistors, 6 and 12 ohms. This time I need to get the power dissipation, power spent, because it has to pass through the resistors R1 and R2. If you remember this from our electrical power lecture, P is equal to V squared over R. I'm using this particular equation because I'm given voltage and resistances. So P1 voltage is 24. Just square that. The resistance for R1 is 6. So how much power is dissipated when the current passes through R1? It's 96 watts. When it passes through R2, rated 12 ohms, it's 48 watts. Okay. Does it make sense that here, passing through R2, which is higher than R1, I have lesser power? Yes, because resistor number 2 have higher resistance, so there is lesser current. Remember, power is dissipated when my current collides with the wires of the atom, right? So if there are lesser current, of course, because of the resistance, higher resistance, there is also lesser power to be dissipated.